be completely online for this section. Okay. I think we only have a few leftover material for queuing theory, but I will definitely have the formal announcement about the midterm exam. Okay, so that can be done online for this section. Okay, but if you are on the other section, okay, I think the instructor can still lecture in classroom. Okay, any question, comments? Do you need a break before we continue? No. Okay. Okay, let me refresh a little bit. Okay, last time we talked about queuing system, right? The concept of queuing system, okay, with three important elements, right? The arrival process, okay, the service mechanism, and of course the queue itself, right? We have seen depending on the details of these three elements, right? We can classify different queues into different types, okay? And the common notation widely used to classify different queuing systems is the Kendall notation, right? Remember that? With five elements, right? First two are for arrival and service mechanism, arrival process and service mechanism. Third one is number of server. Fourth one, capacity of the system. And last one is the system population, right? And we concluded last class with the first rigorous and general result on queuing theory called Little's formula, right? Which express the expected number of customers in the system as a linear relationship with the average time each customer should spend in the system, right? With the scaling factor being the arrival rate, right? And we gave quite a solid justification about Little's formula, remember? And this formula will be quite fundamental and it will be a crucial tool that we will use to analyze upcoming concrete different queuing systems. Okay. So today we make our discussion much more concrete, right? By looking at an arguably simplest queuing system. And I think last class we have discussed a little bit, right? That the first or the simplest queuing system that we should be able to analyze first is the MM1 queuing system, right? In which the arrival process is Poisson, right? With rate lambda, okay? As you may recall from last week, right? This means that the inter-arrival times are independent and identically distributed as exponential random variables with mean being 1 over lambda, right? Because lambda is the arrival rate, okay, in terms of, let's say, customer per second, right? So if the arrival rate is lambda customer per second, you should expect each inter-arrival time to be of rate 1 over lambda, right? Because 1 over lambda is lambda, right? If one customer is arriving at the rate of 1 over lambda second on average, right? Then in the long term, okay, the arrival rate will be lambda customers per second. That's the first M, right? Again, M stands for, the notation M stands for what? Memoryless, right? As we already discussed last week, okay, the Poisson arrival process is memoryless, okay. You can think of it as memoryless because the inter-arrival random times are exponentially distributed, right? The second M for service mechanism, right? Which is also memoryless. That means it's also exponentially distributed, right? But for the service mechanism, it will have another rate determined by the parameter mu, right? Okay, lambda and mu have the same unit, right? In terms of, say, customers per second, right? So the way you should think about it is you can think of it in terms of customer per second or second per customer, right? Incoming is about how fast the customers are arriving into the MM1 queuing system, right? Whereas the service mechanism, right, is about how fast the server in the MM1 queuing system can process subsequent customers, right? So if the service mechanism has a rate determined by mu, so if you think of it in terms of uh, the service time per each customer, it's going to be about on the average, it's 1/mu, right? Second per customer. So if customers keep coming into the server, on average, the server can be done with each customer at the rate of 1/mu second per customer, right? So as you can see, okay, and as we already mentioned last week, right, that for MM1 queuing system to be stable, meaning doesn't blow up, lambda has to be strictly less than mu, right? Because otherwise it means that the customers are coming in faster than the server can handle, right? Then if you run the queuing system for a long time, okay, everything will blow up, right? The queue will accumulate, right? And it will grow to infinity. In addition to that, each customer will have to wait an infinite amount of time in the MM1 queuing system, right? Okay, by the memoryless properties, right? The inter-arrival and service times are all mutually independent, right? Third character 1 signifies that there is only one server, hence one queue, right? But as you can see in this simplest queuing system, there is no fourth and fifth character. That means there is no limit, right, to the MM1 queuing system. So it's idealistic in that sense, right? It means that the queue can accumulate arbitrarily long. Huh? So it's not realistic in that sense, but as you can see, it will serve as a good mathematical model to approximate many real systems, right? What about the last character? It's not there either. Last character is system population, right? But this goes usually with all Poisson arrival process, right? Because one critical assumption of the Poisson arrival process is that the system population is infinite, right? Okay, so now we going to make our discussion much more concrete by analyze fully the MM1 queuing system. To that end, we need to zoom in to the arrival process and service mechanism, right? as you may recall in the derivation of Little's formula, right? We consider two staircase plots, right? AT for the arriving customer, right? And DT for the departing customers, right? And AT is dictated by the Poisson process, whose rate is being what? Rate is lambda, right? And by what we already discussed last week, right? If you consider a very small interval of size delta, right? Size delta. Okay, 1 second. How come I cannot annotate? 1 second. Okay. Oh, okay. I forgot to turn it on. Okay. So interval size is delta, right? And we already know that for the Poisson arrival process, if you consider a small interval, right? The number of arriving customer is Poissonly distributed, right? With parameter lambda times the interval size, right? So in this case is lambda delta. Remember? Maybe I refresh you with the formula for the Poisson arrival process, right? Remember this formula, right? So now, if you want to analyze for a small interval, the probability that within a small interval of size delta, there would be no arriving customer. So you just substitute K to be 0 in that formula, right? So what do you get? Okay. So it's E to the minus lambda delta, right? Because the other part becomes 1, right? So what do you recall of this exponential function? You can use the Taylor series expansion, right? Into the following series, right? And what can you observe? Okay, for in infinitesimal decimally small interval delta, okay, as delta is shrinking, right? Which of these terms are more significant? See, there are infinite terms, right? The first one, of course, is a constant. It will always be there. The second term is a term that is linear in delta, right? What about the rest of the terms? It's super linear in delta, right? So what does it mean? Remember, delta is a proxy for shrinking interval, right? So if you look at the rest of the terms, okay, is super linear in delta, okay, in the context of asymptotic, right? We can see that all these other terms, okay, are going to 0 faster than a linear term in delta, right? So in asymptotic arithmetic, right, all these terms can be denoted with the following notation. little o of delta. What do you think that means? Little o of delta is any term that is going to zero faster than delta, right? So by definition, this means any term by definition, little o of delta is any term by which if you divide it by delta and let delta go to zero, then the term is going to zero, right? To put it differently, okay, as delta is going to zero, okay, the dominant two terms, okay, are the first two, right? One is a constant, of course. The other one is linear in delta. The rest of, yes. In the definition, this can be defined as any quantity, right? So in this case, I'm replacing this by itself, okay? Anything that you divide by the argument, in this case, delta, and still go to zero when delta go to zero is defined as little o of delta. So it's not a concrete number, is any quantity as a function of delta that satisfies this condition, right? And in our context, this little o of delta is everything after the first two terms. Okay. In other words, for a very small interval, right? Probability that there will be no arrival is very close to one, right? Less a linear term lambda delta, right? What about probability that there will be only one arrival? Again, you substitute the formula for the Poisson PMF, right? But now K would be one. So you get this extra term, right? Because earlier is lambda delta to the power of zero, which is one, right? So in this case, K is one. Divided by K factorial is also one. So you get that term, right? And as you can see, it's just the previous probability times lambda delta, right? But you already know that this thing, right, is 1 minus lambda delta plus little o of delta. So if you multiply lambda delta to it, okay, the dominant term is just this linear term, right? Because the other terms are also sublinear in delta, in shrinking delta, right? What about the rest of the probabilities? Probabilities that in a small interval delta, there'll be more than one arrivals. So basically by laws of probability, right, it's just one minus the first two quantities, right? But look at it, you already, if you sum these two up, right, you already get one, right? So if you subtract that from one, the leftover term is sublinear in delta. It's going to zero with shrinking delta faster than any linear term in delta, right? So you can denote that by little o of delta, right? Clear? So in other words, okay, and quite intuitive, as we mentioned, right? Because customers are arriving independently for the Poisson arrival process, right? if you keep shrinking the interval under consideration, right? More and more, you should see either there is no arrival or at most one, right? Because if there are more than one, it's very likely for a very small interval that the arriving customers are colluding, right? But that's not the case for Poisson arrival process, right? All the customers are independent. Okay. So now we get a much more detailed picture about this AFT staircase plot, right? Analogously, we need to get more detail about the service mechanism, right? And you can see that the analysis is quite similar. It's a bit more complex here, but in a nutshell, you get to the same behavior, right? So let's start with the probability that, let's say, when the system is non-empty, right? Meaning there's one customer in the being serviced, right? What is the probability that by uh, by the time of delta second, the server will not be done with the current customer? So as a consequence, right, is d of delta, okay, will not be incremented, right? So what's that probability? How do you calculate that? Again, for the service mechanism, is the exponential distribution, right? So if there's no increment no increment in dt for small delta, that means that the current service time is longer than delta, right? And because you know that tau is an exponentially distributed random variable with parameter mu, you can calculate that probability, right? So now it's just changing lambda to mu, right? So you get to the same expansion that the probability that there's no change in dt for a very small interval delta is very close to 1, except for a linear term mu and delta, right? What about probability that there is one departure within the small interval of delta? Okay, you can do the same analysis here. Okay, by sandwiching the term between an upper bound and a lower bound. So here, in order to be precise with the lower and upper bounds, you need to consider two consecutive service times, right? One is the current one, tau, and tau prime is the subsequent one, right? If there is one departure within interval delta, so that means this first tau has to be within delta, right? And because there's only one, okay, and not more than one, that means the subsequent service time, okay, which is also exponentially distributed with parameter mu, right, has to go after the first one beyond delta, right? So you have this alternative representation of the event where d delta is incremented by 1, right? So now this is a intersection of two events, right? So if you want to upper bound it, you can drop 1. So you get the upper bound there, right? And we want the lower bound, right? Because this is given in terms of lower bound of tau prime. If you want to further lower bound it, you can further reduce this lower bound, right? You can drop minus tau. So you get that lower bound. Okay. This upper bound, right? Look at it. You already know this probability, right? It's 1 minus mu delta plus O of delta. But this is just the complement of that event, right? So this one is definitely mu delta plus little O of delta, right? What about this lower bound? Okay, intersection, but the current service time and the subsequent service time tau prime are independent, right? So you can calculate this probability as products, right? As a product of the two constituent probabilities. First one, you already computed as mu lambda plus little o of lambda, right? What about the second one? Second one, you already computed it, right? It is this much, right? So why do I write it like this instead of 1 minus mu delta and little o of delta? Why do I write it as 1 minus little o of 1? What is little o of 1? No, I would say this is correct, but this is also correct, right? The reason why we write this and not that is because this term, right, is not the whole quantity. We will multiply it with a linear term, right? So that's why if you multiply these two terms, you get a linear term regardless of how you represent this term. Okay, remember O of delta, right, is defined as any term going to 0, right? So what is O of 1 then? This is a definition of little o of delta, right? So what is the definition of little o of 1? So I divide the term by the argument and it has to go to 0, right? But the argument here is 1. So little o of 1 here means anything divided by 1 that is going to 0. To put it differently, this is just any term that is going to 0, right? No matter how fast. So look, this little o of 1 can be this two sums, right? Because this thing, the sum of mu of delta and little of delta is definitely going to 0 as delta is going to 0, right? For this calculation, we don't need to put the whole thing because it doesn't change the behavior, asymptotic behavior of the result, right? Because here is a product of two terms, right? First term is linear in delta. Second term is sublinear, right? Because it's linear times something going to 0. This one is also sublinear. And the last one is also sublinear. So the dominant term is still a linear term, right? To put it differently, instead of putting a shorthand like this, you can put this entire thing, but it wouldn't change the asymptotic of the final result, right? Because the only dominant term is still the linear term in delta with coefficient being mu. The rest are sublinear, right? Okay. So you see a similar behavior, right? With the arrival process. No action, very close to 1. less a linear term with parameter mu now instead of lambda, right? Because earlier it is 1 minus lambda delta. Now this is 1 minus mu delta, right? And the probability that there's one action is linear in delta, but now with parameter mu, right? Because now we're talking about the departure, the service mechanism whose parameter is mu instead of lambda, right? So what do you think will be the leftover probability with more than one departure? It will also have to be little o of delta, right? Because if you sum the first two probabilities, is already close to one less sublinear term, right? So the leftover has to be little o of delta in the same manner as for the arrival process, right? Remember, the dominant one is probability that there's no action, or if there is any action, there's only one, right? Because delta here is very small. The probability that there will be more than one action is small compared to these other two probabilities, right? For both arrival and departure, right? Same form, just change lambda to mu when you go from the arrival process to the departure process, right? Clear? Yes. Which one? This one, right? Okay, so this is like, so here, the assumption, okay, maybe I didn't say the assumption clearly. Assumption here is you start with the 0 is equal to 0, right? So now you want to, and let's assume that, okay, this is 0, this is delta, right? You want to compute the probability that by the time of delta, okay, only one customer has left, right? So how do I represent that? Okay, starting with time 0, the server will start to process the current customer, right? So let's denote that by tau, right? The current service time. So if I know that there is one customer that get done with within time interval delta, what can I say about tau? Tau has to be less than or equal to delta, right? Because if tau is larger than delta, the current customer will stay at the server for the entire amount of delta second, right? So that means the next customer cannot come in, right? So I know that if D is equal to 1, okay, for sure this holds, okay? But it's not the other way around, right? Because I know that D is exactly equal to 1 and not more than 1. What else do I know? So after tau, right, the current customer being serviced will leave, right? But the second one in the queue can come to be serviced, right? And that is denoted by the subsequent tau prime, right? Because incoming customers have different service times, right? Tau and tau prime are independent, right? So if I know that by the interval delta, only one has left, so I already convinced you that tau has to be less than or equal to delta, right? But because there's only one that else was left. Tau plus tau prime, tau plus tau prime has to be larger than delta, right? Because if tau plus tau prime is less than or equal to delta, that means 2 has left, right? But since I know it's only 1, in addition to tau less than or equal to delta, I also know that, right? Because if tau prime is less than or equal to delta plus tau, there must be at least 2 that has left, right? But I know there's only 1 that has left. So this must be true. But this is a lower bound on tau prime. If I want to further lower bound this event, I can relax the lower bound, right? I can drop tau. So I get the lower bound on this probability, right? And asymptotically, okay, the upper bound is linear in delta with parameter mu. The lower bound is also linear in delta with parameter mu. So upper and lower bound matches, right? Upper and lower bound match. So asymptotically, this term is linear in delta with parameter mu. Okay. Yes. The delta is a period under consideration. The service times, they are random, right? We cannot say for sure it's a fixed quantity, but we consider a fixed quantity of size delta. And we want to characterize the probability in terms of delta. Tau is random, tau prime is random, but we know their distributions, right? Their distributions are exponential with parameter mu, right? Delta is a fixed number, right? Under consideration, okay? But we want to analyze the system as delta is shrinking. So we have to write everything in terms of delta in the asymptotic regime. And then we will take limit delta going to 0, okay? Pardon? This one, right? We know tau is exponentially distributed with parameter mu. So we can compute it exactly. Because I convinced you that this event is exactly that event, right? But this event is an intersection of 2 events. If I drop one, I get a larger event, right? Whose probability is an upper bound, right? So let's call this. So this is event B, right? I write B alternatively as, let's say, C intersect D, right? This is an AND, right? Tau has to be less than or equal to delta, as well as tau prime has to be larger than delta minus tau, right? So in other words, B is equal to C intersect D, right? So if I keep only C, then C will subsume B, but C itself need not to equal B, right? So if in terms of probability of B, oh, sorry, yeah, okay. Probability of B has to be less than probability of C, right? Probability C is the upper bound here. This is probability of C intersect D, which is also B, as we already explained. right? This one is probability, right? This is probability. This is probability. I'm saying that this probability will upper bound that probability. Yeah. So I want to compute this probability exactly in terms of asymptotic in delta, right? How do I do that? If I want exact asymptotic, I need to show you that, okay, there is an upper bound and there is a lower bound and they meet in asymptotic, right? So the upper bound is mu delta plus little o of delta. So here this is equal to that. This is lower bounded by that. That is also mu of delta plus little o of delta. So the upper bound is matching with the lower bound. So it must be the asymptotic of the target probability as well. So it's a little complicated, but the long and the short of it is it's the same behavior as the arrival process, right? Because both are dictated by memoryless distribution, right? Exponential distribution. They come with different parameters though. Arrival, lambda, departure, mu, right? So you see these parameters emerging differently for the arrival and the arrival process and the service mechanism, right? Okay, clear? What do you think we do next? Remember, queuing system, you have to consider it as a holistic system, right? We analyze the arrival separately and also the service mechanism separately. Now we have to combine them, right? How do we combine them? Okay. So again, so here is a small detail, but we have to separate two cases. The more usual case is when you start off with non-empty system, okay? Meaning there's already some customers in the system, right? So in which case, there could be either new arrival or there could be departure, right? So that means, remember there are three possibilities, right? In asymptotic for arrival, none, one, or more than one, right? For very small delta. Similarly, for departure, there could be three possible outcomes, right? 3 times 3 is 9, right? So if you consider joint distribution, there are 9 possibilities, right? And how do you compute their joint probabilities? Just multiply them, right? So you already know this is 1 minus mu of delta plus little o of delta. This is mu delta plus little o of delta, right? And this is little o of delta. Similarly, you know here it is 1 minus lambda delta plus little o of delta, lambda delta plus little o of delta, and this is little o of delta, right? So if you want to calculate the joint probability, just multiply them up, right? So let's look at the first one here. What is the joint probability if you multiply these two terms? Again, you want the result in asymptotic, right? So if you consider the non-asymptotic terms, okay, there are 4 resulting, right? 1 and the cross term lambda plus mu delta, And the last term is lambda mu delta square. That's sublinear in delta, right? And if you multiply this to the other terms, it's also sublinear. So you can subsume all the sublinear terms as little o of delta, right? So the resulting probability is 1 minus lambda plus mu delta plus little o of delta, right? So this means after delta second has passed from the initial time 0, nothing has happened, right? No new arrival, okay? No new departure. The system, as a consequence, there's no incrementing in A, there's no incrementing in D, so N stays the same, right? What about this one? This one is when there is no new arrival, right? But one customer has left, right? So if that happens, remember N of T is equal to D of T subtracted by A of T, right? If A of T is 0, D of T increased by 1, so N would be reduced by 1, right? And what would be the probability? You multiply this by that, right? So the first one will be a linear term, mu of delta, minus lambda delta times mu of delta is minus lambda mu delta square, which can be subsumed in this sublinear term, right? And then any other terms are also sublinear, right? Because it will be a multiplication of either of these to a term that is already sublinear, right? So by the same token, if you switch gear from this to that probability, right? It's just like switching lambda and mu, right? Because the form is the same now. You look at the other possibility that there'll be one arrival, but no departure. So that the number of customers in the system would have increased by 1. All right. And then for all these other events, it's very easy to see that their probability will be sublinear, right? Because you start with one multiplying constituent being sublinear already, or this one, right? In addition, this other event also come with sublinear probability, right? Because you start with a linear term for both constituting multiplicants, right? So the leading term would be lambda mu delta square, which is also sublinear. So what can you say looking at these joint probabilities? Earlier, if you look at the arrival process or the service mechanism individually, there are 3 main events, right? The dominating one is there's no action or there's one action. Now, with both arrival process and service mechanism, there are 9, right? 9 possibilities, but which one comes with dominant probabilities? Remember, these are the probabilities, right? So which ones are dominant? term that is not sublinear, right? What are the sublinear term? This is sublinear, this is sublinear, 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 right? So if you consider them jointly, okay, the possibilities with dominant probabilities are these three events. What are they? Either system stay the same, right? Or decreased by one, or incremented by one, okay? And for the latter two, it happens with rate, lambda, and mu respectively, right? And the complement of the sum of these two probabilities is just the dominant term of this other possibility that the number of customers in the system stay the same, right? Okay, let me close with one more slide before I let you have a break, because it's quite heavy, as you can see. Okay, so early on, okay, there was a critical assumption that you start off with non-empty system, right? And zero is strictly larger than zero. What if you start with an empty system? So certainly, okay, if there is no customer in the system, there can be no departure, right? So some options come with exactly zero probabilities, right? So you see, you start off with no customer in the system and there is no arrival, right? How can there be any departure, right? So these two events have exactly zero probability, right? Similarly for this one, if you start off with an empty system and within time delta, there is one arrival only, how can there be more than one departure? That's not possible, right? So this comes with exactly zero probabilities. And because of that, you will see the change in the probabilities of the joint event, right? So here, you start off with an empty system, right? This happens with probability 1 minus lambda delta plus little o of delta, right? Okay. And because there is no arrival, okay, definitely this happens with probability 1. So there is no change in the probability, right? So earlier with non-empty system, remember, this comes with probability 1 minus lambda delta plus minus mu delta, right? But here with the empty system, where there can be no extra departure from the number of customers already in the system, this will change to 1 minus lambda of delta. Okay. This one stays the same. Okay. And this cannot happen because the system starts off empty. As you can see now, only two dominant terms are these two events, right? And their probability sums up to 1, right? Except for the sublinear term. The other events with non-trivial probabilities have sublinear probabilities. So only these two are dominant if you start off with an empty system. Whereas if you start off with a non-empty system, there are three dominant events, right? Okay, why do we need to derive all these probabilities? Okay, because it will help us analyze the asymptotic stationary distribution of the MM1 queuing system. Okay, and I think you all need some break, right? Maybe 10 minutes. Okay, when we come back, I show you how we can use the probabilities that we derive to further derive asymptotic stationary behavior of the MM1 queuing system. Okay. Okay, breaking for 10 minutes, coming back at maybe 2:35 to 35. Analyze all the events, right, with dominating probabilities for the MM1 queuing system, right? So we're gonna use it to further derive asymptotic results for the MM1 queuing system. Okay. To that end, we will use this so-called state transition diagram. Okay. To describe the number of customers in the MM1 queuing system. So how many possibilities are there? MM1, remember, you start off empty, right? Can there be negative number of customers? No, right? Because if there is no arrival, there can be no departure, right? So you have to start with 0 and you can go up with no limit, right? Because there's no capacity in the system. So in terms of possibilities, it's just all non-negative integer, right? And you write that in the state diagrams. Okay. And because of the statistics underlying the arrival process and the service mechanism, right? When you let the MM1 system, queuing system runs forever, right? Of course, there will be, depending on the randomness of the system, right? Customer will be coming in. Some customer are keep going out, right? So there will be fluctuation in the total number of customer in the system, right? But in the long term, we already know the dynamics, right, of the changes of the system, right? So what is that dynamic? Again, the dynamics are the probability that we describe, right? So if you start off with this dynamics, okay, starting with an empty system, what are the two events with dominating probabilities? These two, right? Either no additional arrival and hence no departure, or just one more arrival and no departure, right? This happens with probability close to 1, less a linear term in delta, or a linear term in delta, right? All the other events, okay, namely probability that there would be an increment of the number customer in the system more than 1, would have sublinear probabilities. We can ignore all these events, okay? So as a consequence, if you consider, if you describe this dynamic in terms of state transition in the state diagram, if you start off with 0, the probability that you will go up by 1 is linear in lambda, right? In delta with the parameter lambda. So it's like that, right? Lambda delta with the arrow going from 0 to 1, right? So that comes with this formula, right? You don't need to describe this other probability because it's just complementary to that, right? Because it's just 1 minus that, right? So at 0, the only possible transitioning out is with the rate of lambda, right? What about when you are at a non-empty system? What are the dominating events and what are their transition rates? Remember we talked about it, right? So for this one, the event whose probabilities are dominating are only these 3, right? Okay. What about this one? Where am I transitioning from N0 to N0 plus 1, right? And that happened with rate lambda. What about this one? I'm transitioning from the current state to the current state less 1, right? That happens with probability with rate mu, right? How do I represent that? In the state transition diagram, that is for all non-zero states, right? So let's say you zoom in to 1, let's say 1, you see a transitioning rate of out to the next one of rate lambda, transitioning back down with rate mu, right? And that happens to all states, right? Even if you go to 4, there's still 2 arrows coming out, right? Going up with rate lambda, going down with rate mu. And that makes sense, right? Because how can you go up when there is a new arrival, right? That happens with rate lambda. How can you go down when there's a departure, right? And that happens with rate mu, right? Correct? So you see this uniform behavior from state 1 on. For state 0, of course, because you already start off empty, that you cannot go down any further. So you can only going up. And that happens with rate lambda. Right? And again, because the other dominant event, right, for non-zero states happen with the complementary probability 1 minus lambda plus mu delta. So I don't need to write the arrow coming back to itself. Remember that event under that dominating event, the number of customer in the system stay the same, right? So here for this dominating event, right, the number of customers stay the same. Similarly for this one, right? So if I were to write any arrow, it's like coming back to the current state. But because this one has complementary probability, I don't need to write it. So I can describe the rate of transitions for different states of the MM1 queuing system using this state transition diagram, right? And the way you should think about n of t, right? is just like a random process, right? That when you keep it run for a long time, right? Then it's like N of T will be hopping through these states, right? With the underlying statistics for the arrival and arrival process and the service mechanism, right? The former happens with rate lambda, the latter happens with rate mu, right? So in the long run, what do you think? What do you think will happen to this random process describing the number of customer in the system? It will settle, right, into the so-called stationary distribution. So in a sense that if I let the state runs for a long time, right, then different states should come with certain probabilities, right, that will sum up to one, right? And these are called stationary probabilities. These are the long-term probability, P of I, right, for all the states. And you can think of this probability as being the frequency on average that the system will be on that state, right? So it's still a probability, right? So they have to sum up to one. Okay. So now our goal will be to derive these stationary probabilities. Okay. What type of condition do you think these stationary probabilities should satisfy? So remember, in a stable system, okay, the random process NT should be able to hop along all these states, right? So what type of condition you should think this probability should satisfy? There should be some balancing going on, right? It's like when you consider certain type of fluid flow or something like that, you know, if you consider it for any states, right, these probabilities should satisfy global balance equation. What do I mean by that? It can be described basically simply as for each state in the state transition in the state diagram, once I take into account the stationary probabilities, the total frequency going out should be equal to the total frequency coming in. Okay. What do I mean by that? I know the transition rates, right? Now I want to determine the native rates of the different states themselves, the P of I's, right? The global balance equation is about total frequency going out equal to total frequency coming in. For example, if I consider the zero state, what should be the total frequency going out? Remember, lambda is a transitioning rate, right? But I have to account for the native rate of being in zero, right? So in this case, going out is, so let me say going out is upstairs. Coming in is downstairs. For the zero state, what should be the total frequency going out? Should be P0 times lambda, right? Because lambda is already transitioning. But if I want to account for the native frequency of being in state zero as well, I need to account for zero. What about coming in? How can I come into the zero state? only from state 1, right? Because for small interval, dominant event is to coming in from 1 only, right? So that happened with rate P1. What about a what about a positive state I? What is a total frequency going out? Going out of I. So I can go out of I in two ways, right? Going to I plus 1 or going down to I minus 1. So that happened with rate, right? How can I come into state I? Coming in Pi plus 1 times mu, right? Coming in from I plus 1. Or I can come in from I minus 1, right? And the claim is that this going out equal to coming in has to happen at all states. Why? Why should that happen? To justify this, I need to ask what would happen if at any state there is a strict inequality, right? So let's say, what if for some state, okay, there is a strict inequality of going out larger than coming in? What will happen? What do you think will happen? Let's say at this state, okay, let's go back. Let's say what would happen if at this specific state, going out is larger than coming in. What do you think will happen? You will visit for less and less, right? As you keep the system running, right? And that would be like P4 will be going to 0, right? So what do you think if P4 is going to 0? If P4 is going to 0, then because transition is only by 1, increment of 1, how can you reach P5, P6, and so on, right? So that means in the long run, if going out of P4 is larger than coming in to P4, eventually P4 will go to 0. And if you start off at 0, it's like you only confined to this state. Do you think that's the case for MM1Q? That cannot be, right? Because the system is random, okay? If you let it run for a while, for a long time, you should be able to visit all states, right? Similar to the inequality in the other direction, right? What if going out is strictly less than coming into P4? What do you think will happen in the long run? System will start to accumulate on P4, right? Only. So that means like P4 is going to 1. So it's like if you keep the system running for a long time, eventually there will be 4 customers only. That cannot happen, right? For the realistic system, MM1Q. So that's why at all the states, you must have the global balance equation, right? Okay. So I already written down the global balance equation for each state. Let me remind you again. For the first one, going out, okay, is P0 lambda, right? You can only come into the 0 state from 1. That happens with rate mu, right? For all the other states, okay, the pattern is the same. You can go out of a target state in two ways, right? Going up or going down with rate lambda or mu, respectively. You can come into it from above or below, okay? With rate mu and lambda, respectively, okay? So this pattern recurs for all other non-zero states. So now you have a system of infinite equations, right? Describing the global balance equation in terms of the stationary probabilities that you want to derive, right? Remember, lambda and mu are parameters of the system, okay? We have shown you that in the long term, system will stabilize, right, into the stationary distribution, the P's, right, described by the P's. Now we have to derive these P's, right? And the way we do it is by using this system of infinite equations to derive the P's. After we get these infinite equations, how do you think we should proceed? Do you see any pattern? Do you see any pattern of how we should proceed? What do you do when you have system of equations? You do to solve the equations, right? So now, remember when you do it in high school, right? You have a finite number of equations, right? That describe the relationship among different variables. How do you start when you have system of equations? If you want to solve for the value of the variables in the system of equation, typically, how do you start? You do you simplify, right? How do you simplify? You do certain type of systematic eliminations, right? To get simplified set of equations to enable you to solve the equation system easier. Can you suggest any elimination here? Do you see any pattern? Do I see the first line in some part of the second line? Let's say I keep the first line. Can I use the first line in the second line? You see this part, and that part, right? It's just a switching of the sides, right? But I already know that lambda P0 equal to mu P1 from the first line. These terms appear on the second equation as well, albeit on the different sides, right? So why don't I just cancel them? Because I already know they are equal from the first equation, right? So what do I get when I do the cancellation? Lambda P1 mu P2, right? So I simplify the second equation using the first equation, right? Can this pattern recur? So now I start from the first two equations. Now I keep this one. Second one I simplify, right? But then there are many more equations. Again, pattern is the same, right? I see this simplified version of the second equation in the third equation as well, right? Albeit on different sides, right? So why don't I cancel them as well? So what do I get? So now do you see pattern? You see any pattern? It's just the same pattern, right? So you see lambda EI. Right? So the subsequent P's follow the same relationship described by lambda and mu. Right? To put it differently, okay? Now the system of equations are simplified to the same pattern, right? And because of that, when I go from PI to PI plus one, right? It involves a multiplication by a fixed factor lambda and mu, right? So now I can describe each pk in terms of p0, right? By this geometric factor, okay? So now to solve for all the p's, I just need to solve for, now that I describe all the p's in terms of p0, so now to solve for all the p's, I only need to solve for p0, right? How do I know p0? Remember, these are probabilities, right? So what happened to probabilities? They must sum to one, right? So if I sum them up, okay, they must sum to one. Okay, do you remember this sum? 1 plus rho square, where rho is defined to be lambda divided by mu, right? So I know that the sum of all these stationary probability is 1. I can write it in terms of P0 like that. And what is this sum? 1 plus rho square. Do you remember that it is that? Remember, we in a stationary system, right? Lambda strictly less than mu. So rho is strictly less than 1. So this sum is finite and is equal to 1 over 1 minus rho. How do I prove that this is equal to 1 over 1 minus rho? Do you remember? Oh, let's call this S, right? So what would happen if I subtract S by rho of S? What happens if I subtract S by rho of S? Let's call this S. S is 1 plus rho square and so on, right? What is rho S? It's just like this term each multiplied by rho, right? So what is that? Instead of starting with 1, I start with rho. What happens if I subtract them? Remember, both goes on forever, right? Whatever happened here will happen here as well. It's just one term earlier, right? So all the other terms are cancelled except for this one, right? So that means 1 minus rho times S. S minus rho times S is equal to 1, right? So then S must be equal to 1 over 1 minus rho, right? and that is S, right? Okay, now that I derive P0 to be 1 minus rho, then I know all the PKs, right? Because the PKs are just rho to the K times P0, right? Now that I know that P0 is 1 minus rho, I know all the PKs, right? Clear? Okay, let's look at these stationary probabilities as a function of rho. So do you see? So how can you explain this? Okay, starting from the top left with a very small rho. What does small rho represent? Small rho. Small rho means the server is much quicker than the arrival rate, right? So you see lambda is very small compared to mu. So you see that probabilities are concentrated at uh, low numbers, right? The closer you go to 1, right? The longer tail the station probability represent, right? Represents stationary distribution represents. Okay, that means it's more likely that the system will go larger, right? Because if the incoming rate is faster, okay, almost catching up with the rate of the server, um, each customer will have to wait longer and longer, and it's more likely that the system state will accumulate, right? So again, we only consider stable systems, right? That means lambda has to be strictly less than mu, right? Otherwise, what will happen is lambda is larger than mu. System will be unstable, right? Everything will blow up, right? And all the analysis that we describe will fail, right? Having derived all the stationary probabilities, okay, we can use it to derive the average number of customer in the system, right? Just use the probabilities to compute the expectation, right? So these are the probabilities, right? To compute expectation, you just multiply by the number of customer in the system. So what is that sum? So again, you come to this form, right? How do you derive that sum? So the claim is that this sum is equal to that, right? Do you recall how to derive that? Okay, same trick, right? Let's call it S. How can I derive S? Just write it out. S is equal to rho plus 2 rho square plus 3 rho third. Okay, now I want to define an equation that will describe S, right? So what do I do to S? Same trick, right? What if I do S minus rho S? What will happen? S is this term, right? What about row S? Row square plus 2 row third plus 3 row fourth. What happens if I subtract them? First one is row. Second one, because of this progression, right? When I subtract, I will get row square. Similarly, row third, and so on, right? But you already know what this sum is, right? What is that sum? It's the same sum that we encounter, right? This, you take row out, it will just be this geometric sum, right? Of row, the power of row. What is that? That is 1 over 1 minus row, right? So if 1 minus row S is equal to that, what is S? S is row by 1 minus row square, right? Correct? So 1 over row cancel 1 over row square. So you get expected number of customer in the system to be row by 1 minus row, right? Yeah. What do you think we should do next? After we derive the expected number of customer in the system, what do you think we should do next? Remember, little formula, right? We can invert it, okay? Now that we know E of n, if little formula says E of n equal to lambda E of t, right? But if we invert it, we already know E of n, we can derive E of t. Expected time each customer will spend in the system. Remember, in MM1 queuing system, there's one queue and one server, right? This expected time each customer spend in the system will consist of two parts, right? The first part is the waiting time to go to be served. And the second part is the service time, right? We already know the expectation of the service time, right? According to the exponential distribution with parameter mu. What is this E of service time? This is 1 over mu, right? The first part is from that formula. So you can compute the expected waiting time only, excluding the service time. What will you get? You get 1 by mu minus lambda subtracted 1 by mu. What is that? That is equal to lambda divided by mu times mu minus lambda, right? Okay. So now that you compute the expected wait time, another interesting side effect is what? Now that you compute the expected wait time, remember MM1 queuing system is like this, right? There's a queue connecting to the soul server and the arrival is coming in here, right? Okay, the little formula is for the entire system, right? This is coming in at rate lambda. This entire time in the little formula is for the entire system, right? That's why T, which is equal to the wait time plus tau, is the time in the little formula, right? The waiting time is only for which part? Waiting time? Waiting time. The waiting time is only in the queue, right? Excluding the service time at the server. So what would happen if you only apply Little's formula only to the queue, excluding the server? If you apply Little formula only to this subsystem for the MM1 queuing system, the resulting number of customers in the system will only be the number of customers only in the queue, right? Excluding the number of customers that is being serviced. So the relationship for the Little formula applying to the queue only will be that, right? So now that you already know expected wait time in the queue only, excluding the service time, you can use this sub Little formula to compute the expected number of customers in the queue, excluding the number of customers being serviced, right? That's NQ instead of N. So what is that? You already know expected wait time here, right? Multiplied by lambda, so that's lambda square by mu and mu minus lambda, right? And that is rho square divided by 1 minus rho. So notice that that is less than E of N, right? Because NQ is upper bounded by N, right? But it could be less than N because NQ, when there's one customer being serviced, N will be NQ plus 1, right? When there's only one customer, NQ and NQ will be 0, right? N will be 1, okay? Right? But when the system is empty, both NQ and N will be 1, will be 0, right? So that's why you subtract them is not exactly 1 because it depends on the probability as to when the system is empty out, right? Because when the system is empty out, both NQ and N are 0. Okay. So this sub Little formula is interesting because if you go back to this staircase plot, right? You can overlay another staircase plot in orange. Okay. What should this orange plot represent? Remember, staircase plots are used to derive Little formula, right? Now that we apply Little formula to only the queue, right? Then we cannot consider the original DT anymore, right? Because that DT is going out of the system entirely, right? That is DT, right? This is AT. But now that we consider a subsystem only in the queue. We have to change from DT to another staircase pod. Let's call it O of T of the customers leaving the queue going to be served, right? And that is what the orange part is about. Right? So you can see for the first customer, since the system starts off empty, right? When he comes in, he doesn't have to wait at all. He going to be served directly. That's why you see the orange curve incrementing right away, right? And this whole thing is the entire service time for the first customer. For the subsequent customer, when they arrive and there's already someone in the system, first they have to wait, right? First they have to wait. That's the area between the red and the orange curve, right? And then once the server is ready, the subsequent customers will go to be serviced. That's the area between the orange curve and the original blue curve DT, right? So when you derive the little formula only for the queue, you replace the original blue DT with the orange OT. Okay. So when the system is empty out again here, it's like you resetting the system. And as a consequence, the 7th customer, when he comes in, does not have to wait anymore, right? Okay, let's close the MM1, conclude MM1 queuing system with a concrete example, okay? Representing a barber shop, a shop, let's say, with one cashier serving customers. Lambda is a half customer per minute. In other words, each customer should take 1 over lambda, that is 2 minutes. The server is faster. When non-empty, it can serve 4 customer per minute, right? So you know lambda, you know mu. It's an MM1 queuing system. You know everything about the system, right? Because what is E of N? You remember the formula for E of N? What is the formula for E of N? Lambda, rho divided by 1 over rho, right? So what is that? Rho divided by rho divided by 1 over rho. What is that? Rho is, what is rho? Hmm? What is rho? Lambda is a half. Mu is 4. So what is rho? Rho is 1/8, right? So it's 1/8 divided by 1 minus 1/8. What is that? 1/7, right? Knowing expected number of customers in the system. How can I derive expected time each customer should spend in the system? Little formula, right? This is equal to E of n divided by lambda, right? So that 1/7 divided by 1/2. That 2/7. E of NQ, how do I derive that? E of NQ. Remember this formula? Row square divided by 1/row, right? So I already know row by 1/row to be 1/7. E of NQ is multiply that by row, right? Which is 1/7 times 8, 1/56, right? Knowing E of NQ, how can I derive the waiting time? Again, little formula only to the Q, right? So that would be E of NQ divided by lambda, right? 1/56 divided by 1/2, that 1/28, right? Utilization factor, how do I define that? It's a frequency in which the system is not idle. How do I compute that? 1/1 minus P0, because P0 is the only event where system is empty, right? When it's not empty, server is utilized. So what is P0? We already know that is 1 minus rho, right? So that is equal to rho, which is 1/8, right? Simple. As a consequence, 7 of 8 times, system will be underutilized. Okay, another very straightforward example, clouded by just jargons, right? So here is the example of messages incoming to communication line. Okay, incoming rate is 240 messages per minute. Okay, the outgoing rate is 8,000 character per second. Okay, so now you just have to normalize the two rates. If you want to describe the incoming rate in terms of message, right? Then you need to take into account the average number of characters per message, which is 176 for the outgoing rates. 176 here, because 800 is measured characters per second, but lambda is in terms of message. So you have to account for the average number of characters per message. And then you normalize the time, okay, between minute and second to get lambda and mu of the same unit of message per second. After you know lambda and mu for the same units, you know rho. Once you know rho for MM1 queuing system, you know everything, right? Because everything can be described as a function of rho, lambda, and mu. Any question, comments? That will conclude our discussion for the first queuing system. Okay, let's try to finish the second one. Now we just add an extra element, right? Which is the fourth character here, K. What thing is K? K is capacity, right? So what do you think will happen to the state diagram with this capacity limit? So you cannot keep going forever, right? You are capped at K, right? So what will happen if system is already full and new customer has arrived? What will happen for an incoming customer when the system is already full? That customer will be rejected, right? But because of the probabilities that we have derived, the transition rates are still the same, right? And the global balance equations are still the same, except that now we have only K plus one of them, right? Instead of infinitely many of them. But we can still cancel the terms, right? Yeah. Okay, from the first one, we cancel that term, right? And then for the equation for state 1 to state 2, we can cancel these terms, so on and so on. Okay, until we get this system of equation. Now it wouldn't go forever, right? But the P's still exhibit this geometric relationship in terms of rho. Now, the condition for P0 will be different because there's only be P sub to PK, right? So you look at this sum, it will be a finite sum. Using the same trick, you can derive the formula for this sum to be equal to that, right? I leave you to derive this, but you can use the same trick, dividing this sum as S, okay? And use the relationship to derive an equation describing the suitable relationship for S. And now that you have P0, you have all the P's. So notice that now that the system is capacitated, okay? And some customers coming in when system is full are rejected, then there'll be no limit to the range of lambda and mu anymore, right? Because even if lambda is larger than mu, system cannot go beyond K. So it will not blow up. So now rho can be anything, right? In particular, when rho is 1, lambda is equal to mu, all the P's are the same, right? So you see when rho is equal to 1, all the P's are equal, right? And because there are K plus 1 states, each P is just 1 over K plus 1. You can derive all these stationary probabilities. You can see that the for rho less than 1, it will be decreasing. For rho larger than 1, it will be increasing. Okay. Once you derive all these P's, okay, then you can derive the average number of customers in the system, right? Because it's just the expectation in terms of these P's. Formula is a bit complicated. I leave you to fill in the detail. but I just want to point you out to a phenomenon that is unique to this MM1K that is not present in the MM1 queuing system. What do you think is that phenomenon? Is there any rejection for the incoming customer in the MM1 queuing system? There is none, right? But for for a capacitated system, there will be some rejection. What do you think is the implication of that rejection? Remember, when we apply the Little's formula, right? Customer are coming in with this rate, right? Right? And we describe expected number of customer in the system in terms of expected time each customer spend in the system. When we derive Little formula with AT and DT, did we consider any rejection? No, right? So now that there is rejection, how do we have to modify the Little formula? Because remember, for rejected customer, right? He or she will not enter the system at all. That means the AT will not be incremented, right? And in addition to that, it will like that incoming customer completely disappear from the arrival process, right? So we need to account for this rate of rejected customer, right? In the Little formula to be able to apply Little formula precisely. So when customer can be rejected, it's like the incoming rate lambda is split into the one that is accepted and the one that is rejected, right? So when we want to compute the average number of customers in the system in terms of average time each accepted customer spend in the system, we need to discount the incoming rate accordingly. And what do you think this effective rate is? What is the discounted rate when the customers are being rejected? What is the probability that when the customer arrive, the system is already full? It's precisely this PK that we already derived, right? Because for when the system state is not equal to K, the system can accept an additional customer, right? This discount is 1 minus PK. And you have to use this effective lambda in the Little formula instead of the original lambda. Okay. And that is what you will use to derive expected time each accepted customer spend in the system. Okay. So you can see the effect of this capacity limit on the effective incoming rate, right? So here the x-axis is rho. So here mu is fixed to be 1. So this rho depends on the varying lambda, right? And we vary the k's. So you see the larger the k is, the more likely the incoming customer will be accepted, right? So you see a larger effective rate. And that will translate to larger expected time each accepted customer will spend in the system. Okay, before we conclude for today, okay, we will consider a concrete example with a fixed capacity limit. So here, row is 2 by 3. And let's say we capacitate the system with 3 customers. This is an example with a barber shop, okay, with the capacity of 3 customers. So that means why the sole barber is cutting, the barber shop can only accept 2 waiting customers, okay? Can only accept 2 more waiting customers. So you can use this row in the formula to compute the probability that the system is full to be 0.123. And then you can use the formula to compute the expected number of customers in the system. So you can see here because row is still less than 1. So you see, even though system is capacitated at 3, the expected number of customers in the system is still a little above 1. Now that you have computed P full, P3, you can compute the according effective incoming rate, right, by discounting for PK. Okay, so here, even though lambda is 2, right, when you discount it with the event that a customer can be rejected, then it becomes 1.754. Now that you have computed the effective incoming rate, you can correctly apply the little formula to compute the expected time each accepted customer spend in the system to be a little more than half an hour. And because you compute all the P's, right, you can compute the probability that the system is empty as well to be about 41.5%. So here's another interesting way to compute number of customer waiting, okay, NQ from E of N, right? So as I already mentioned, N, okay, is what? N is total number of customer in the system, right? So in this case, number of customer waiting plus an indicator function, right? When system is what? It is 1 when. So what is NQ? In term, what is this probability? When the system is non-empty, what will happen? There will be some NQ, right? When the system is empty, the sole customer will go to have his or her hair cut directly, right? So when I compute this E of NQ, I can write it as n subtract that by indicator function of system non-empty, right? Because what will happen if the system is empty? When the system is empty, this will be 0, right? When the system is empty, NQ is equal to N, right? Because that's so customer can go to be served directly. But when the system is non-empty, the extra customer will have to be waiting. So when I compute NQ like this, I can subtract E of N by the probability that the system is non-empty, and that is 1 minus P0. That is when I can compute E of NQ from E of N, right? Because when I write it like this, 1 sys non-empty, what do I mean by that? There are two separate cases, right? When the system is empty, this means this indicator function is 0. So that means NQ is equal to N. When the system is non-empty, NQ is equal to N minus 1. This is when empty. This is when non-empty, right? Okay. So now it's also instructive with the capacitated system, okay, to compute this utilization factor, and that will be equal to the probability the system is not empty, right? Because when the system is empty, the barber will not be utilized, okay? You can see from the formula that this is equal to rho effective, that is lambda effective divided by mu, to be that quantity. And now that you derive the number of customer in the queue, you can apply this sub little formula only to the queue, okay? Using the effective lambda instead of the original lambda, right? So you can see that from MQ, you can compute expected time each accepted customer will have to wait, and it will be about quarter an hour. Okay, remember in this case, we consider lambda equal to 2, mu equal to 3, with rho being 2/3, right? But because of the capacity of the system, we need to discount the incoming rate of 2 to 1.75, okay? So now it will be instructive to compare this capacitated system to 3 with an uncapacitated system. Remember, for an uncapacitated system, lambda doesn't have to be discounted, and rho will be the full lambda divided by mu, and that lambda divided by mu, which is 2/3, is also equal to the utilization factor, right? For the uncapacitated system, right? And that 2/3 is 66%. So now that we have a capacitated system, okay, um, even though it looks like, okay, because now that we have to reject certain customer, so there's a probability that the arriving customer can be accepted to be served in the future that was discounted, right? So that's why you see the decrease in the utilization factor, because the customers that are rejected will never be served, right? So that's why you see this utilization factor going down from the uncapacitated system about 66% to a little below 60%. Okay. Just for the consistency check, okay. Now that you derive E of n from the formula that we showed earlier, right? We can double check that by compute all the P's in the brute force manner. We already know P0 and P3, right? We can later compute P1, P2, and then use them to compute E of n in a brute force manner and verify that it is equal to the value that we already computed from the prior formula. Okay. So, so to conclude, today we start off with the simplest queuing system, right? MM1 queuing system. Okay. And we derive the global balance equation, right? Which is the basis of how we can derive the stationary probabilities, right? Which is the basis for all the computation of performance metrics for the MM1 queuing system, right? MM1 queuing system is idealistic because it's not capacitated, right? Then we switch to the second queuing system by introducing the capacity. When you see a new phenomenon of customer rejection, that has to be properly discounted, right? When the arriving customer come in when the system is full, right? And you see that will lead to certain reduction in the utilization factor from the uncapacitated system for the same role, right? Because for the uncapacitated system, all incoming customer will be accepted and eventually will be served, right? Because they can wait arbitrarily long. But for the capacitated system, you already reject the chance of future service for customers that are coming in when the system is full. Okay, that's why you always see the reduction of utilization factor from the uncapacitated system to the capacitated system for the same traffic density or row. Okay, simply because of customer rejection. Okay, what do you think will be the next queuing system that we will consider? We go from idealistic, simplest MM1, introducing capacity, right? But still, for the two queuing system that we consider, there's only one server. Next, we will introduce you to another queuing system with more than one server. But we start off idealistically with no capacity as well. Okay. Okay, I think next week, again, I stress that for section 1 only, class will be completely online. Okay. So please join by Zoom. And we almost done making the midterm exam question. By next week, we should have all the detail of the midterm exam to announce to you. Okay, any question, comments?